So our example for this is going to be from section 2.2, problem 1. And it says to solve 1 plus x dy minus y dx equal to 0. I'm just going to put that thing in a box. My lines aren't straight enough. Okay, so first up, so if we rearrange this whole thing algebraically, we could kind of see that this is dy dx is equal to y over 1 plus x. So this is a separable equation because we've got our first order equation and we've got kind of our h of y and our g of x both there. So you don't have to do this every time you decide to solve something as a separable equation. I just wanted to make sure that you recognized why it's separable and we're going to be able to solve it this way. And so our first step is just going to be to rearrange it so that we have all the y's on one side and all the x's on the other. So if we start from dy dx equal to 1 over 1 plus x times y, all I did was separate out the x and the y parts. Then we can rearrange it to dy over y is equal to dx over 1 plus x. All I did was I moved my dx over there and my y over there. Did I draw my arrows right on the previous slide? I did. Cool. Okay, so now that I've done step 1, move variables to opposite sides of the equation. I'll do a little 1 right there so you know that that's what happened. Now I can move on to step 2. I'm going to try to integrate both sides of the equation. So I will go ahead and say that I have the integral of dy over y is something that I want. But that's just going to be the natural log of the absolute value of y. I could say plus a constant will, I'll show you that the constants go away and then I'll stop doing that later. And then the integral of dx over 1 plus x, kind of same thing. I'm going to have the natural log of 1 plus x plus a constant. But it's different from the other constants, so I'll put a little hat over it. Actually, I'll just do that one. I'll call that constant k. And yeah. So I'm going to have natural log of y plus c is equal to natural log of 1 plus x plus k. And that was step 2, integrating things. And these two unknown constants are both just random numbers that I don't know. And so I can combine them into one common unknown constant that I'll just call C1, where C1 is just K minus C, but K and C don't have special meaning to me, so I don't want those things here. The reason I did this is because when you have an initial value problem for a first order differential equation, you're only going to have one initial condition. So you can only solve for one constant. So you can't find C and K separately. You're just going to be able to find the one constant that represents the relationship between them. Anyhow, I can go ahead and sort of try to solve for y. So I just take the exponent of both sides. So like I have e to the natural log, e to all that stuff. So e to the natural log of y is y, and e to the c1 plus natural log of 1 plus x is going to be e to the c1 times e to the natural log of 1 plus x. So that's just going to be that y is equal to some new constant. I'll call it c2, I guess. times 1 plus x. And so what we haven't done is we haven't sort of used initial conditions to solve for the unknown constants. I guess I omitted a step when I was writing all this. So I'll just call it step 4 because these two things could kind of go in either direction. But what I did first, since I had no information to solve for C, is I wrote y in a neat way. I solved for y in a way that I would like to see it. And now I'm going to pretend like we had initial conditions so that we could go ahead and practice that third step. So we're going to say this is example continued. And we're going to imagine that instead of being given just a differential equation, we had been given an initial value problem. So we had that 1 plus x dy minus y dx equals 0. That's the same as we had on the previous slide. And then imagine we have an initial condition, y of 0 equals 4. So we have the solution, y equal to C2 times 1 plus x. We know that y of 0 equals 4. So this is something that you've practiced in your web work already. We're just going to have that we want 4 to be the same as y when we plug in 0. So we want it to be C2 times 1 plus 0. So 4 is C2. So the solution is just 4 times 1 plus x. Like that. And that would be step 4, using the initial condition to solve the initial value problem. Now, real quick, I just want to roll back, look at our two parts of this example and kind of make sure that we're on the same page with some vocabulary. So on this first page, I was solving a differential equation. And when somebody wants you to do that, they're going to ask you for the general solution to the differential equation. So what we did was we found the general solution, y equals C2 times 1 plus x, that solves the differential equation, 1 plus x dy minus y dx is equal to 0. What we did on the second page was we solved an initial value problem. So we're not finding general solutions anymore. On this page, we found the solution to the initial value problem where y of 0 equals 4 and the differential equation is the same as before, and it's y equals 4 times 1 plus x. Difference is when you find general solutions, you're going to have unknown constants. You'll have as many unknown constants as the order of the differential equation. You can just ignore that fact until we get to exam 2 when we actually have to worry about that. Just for now, general solution means unknown constants. Solution to an initial value problem doesn't have constants. Constants replaced by 4. So when you solve an initial value problem, you plug in extra numbers and you get rid of unknown constants. You replace them with numbers. That's just like a little detail that I think can be a little hard to kind of work around. So I just wanted to make sure to bring it up right now. In the next video, we'll go ahead and work through some more examples that deal with initial conditions in different ways. And we'll kind of highlight why you can switch the order of dealing with initial conditions or solving for y.